be scientifically literate is to empower yourself to know when someone else is full of bullshit. Neil deGrasse Tyson. So let's get clear on some topical science. I'm going to talk about vaccines today. So there's been a lot of theories about why people get sick, from demons to bad air, poor circulation to germs. Now, to put things in perspective, according to the World Health Organization, the two most common causes of death in the world are heart attack and stroke. And for the most part, we can blame those on things like genetics, lifestyle, and diet. Now, there's no vaccine for heart attack or strokes, but there are vaccines for germs. So for this video, when I say germs, I'm talking about things that are smaller than we can see by the naked eye, but also cause disease in humans. That means fungus, bacteria, viruses. We're mostly going to talk about bacteria and viruses because they cause more diseases in humans than funguses do. Now, an Italian scientist by the name of Agostino Bassi was the first to prove that diseases can be caused by a germ. Between 1808 and 1813, his experiments were able to demonstrate that a fungus was causing disease in silkworms. This was a big deal at the time because the disease was causing a lot of problems for the French silk industry. Now, in experiments that he did about 50 years later, between 1860 and 1864, French chemist and microbiologist Louis Pasteur was able to demonstrate that germs also cause disease in humans with puerperal fever. Puerperal fever is an infection of the reproductive organs that usually resulted in death, and at the time nobody realized it, but most women were contracting this disease during birth or miscarriage from the medical practitioners that were trying to help them. Not all diseases are caused by germs, but German physician and microbiologist Robert Koch designed 4-point criteria that allowed him to prove specific germs cause specific diseases. Today we don't need to meet all 4 of those criteria to prove that a germ can cause a disease, but this was an important step because at that same time, Koch and other scientists like him were able to identify carriers. These are people that had germs for diseases like cholera and typhoid fever that weren't getting sick. Scientists also identified plenty of other bacteria that didn't ever seem to cause people to get sick. So Koch and others like him were able to prove that most bacteria don't make people sick, and for the ones that do, they don't always make people sick. And at the time, he couldn't understand why. Now, bacteria are prokaryotic cells, and what that means, among other things, is that there's not an organized nucleus where their DNA is in their cells. They're also much tinier than our body cells. We have bacteria all over us, on the outside and inside of us as well. And if you were to count up all the bacteria cells in your body right now, there'd probably be 10 times the number of bacteria cells as you have body cells. But they're so tiny that if you were to take every one of them out of your body and put them in a gallon jug, it would probably only fill that jug halfway. Bacteria usually live in the spaces between your cells and your gut and on your skin. They reproduce by growing larger and then dividing in half. Now, like I said, not all bacteria cause disease. Some bacteria play a really important role in your digestive system, in your immune system, but the bacteria that can make people sick usually do so either directly when they're growing or through some toxins that they release while they grow and reproduce. So we call the bacteria that do cause disease germs, and germs are responsible for a number of well-known diseases like tetanus, typhoid, syphilis, cholera, food poisoning, tuberculosis, and then a couple of nasty bacteria, staph and strep, cause a variety of infections in humans. Viruses are very different. They're much, much smaller. They're probably the most common form of biology on Earth, and they even infect bacteria. Viruses are pretty much just small bundles of RNA or DNA inside of a membrane or an envelope. Viruses can't reproduce on themselves, so their whole goal is to get inside of a cell and then trick that cell into making copies of it. So when somebody gets sick with a virus, what's happening is the virus is getting inside their body cells and tricking their body cells to make many, many copies of it. Eventually, the cell has so many copies inside that it actually explodes, releasing the virus into the rest of the body. Viruses are responsible for a lot of diseases in humans like the common cold, the flu, chickenpox, Ebola, SARS, and HIV. Now, the immune system is incredibly complex with many, many levels and types of responses. To describe it real simply, I'm going to compare it to the military. So the immune system starts with basic training. That's our bone marrow. The bone marrow is the source of all blood and immune cells in the body. That's why when someone has leukemia, one of the first symptoms is elevated white blood cell counts. After being born in the marrow, our immune cells will mature in the thymus. Next are the military roads and forward bases. These are the lymph vessels and nodes. Now, lymph is a fluid that gets circulated around our bodies like a sewage system. The lymph vessels are the roads or the pathways that lymph takes. Our immune cells move through these passages, and they'll even congregate at lymph nodes while they're building up their forces to fight infections. And that's why you might have swollen lymph nodes whenever you get sick or have an infection. When it comes to fighting bacteria and viruses, there's 2 main frontline immune cells. That's the B lymphocyte and the T lymphocyte. We're going to call them B cells and T cells. Now, the B cell is kind of like a scout soldier. They do reconnaissance. They're looking for anything that doesn't belong in your body. They make something called an antibody, and that's like a marker for things that don't belong. So what a B cell does is if it finds a germ in your body, it's going to mark it with the specific antibody for that germ if it has it, and it's going to tell another part of the immune system to take care of that germ. What this means is B cells are very specialized, so they have specific antibodies, and those specific antibodies will only mark specific germs. T cells are more like heavy artillery tanks. They're not as good at finding germs, but they deal a lot of damage when they find them. T cells are especially good at dealing with cells that have been infected with viruses. So remember, viruses take over a cell and use that cell as a virus manufacturing facility. T cells, as long as they know a cell is infected with a virus, will actually devour that cell before the virus has a chance to reproduce and spread. So there's lots of other components to our immune system, but these are the two frontline cells. They're constantly vigilant, looking for anything that doesn't belong in your body, and then they attack or they tell other parts of the immune system to attack. Now, what's especially interesting about these cells is B cells actually have a memory. So once they've found a germ and they've found the antibody that goes along with that germ, they keep some of those antibodies around for future reference. And what that means is if you encounter the same germ down the road, your B cells will recognize it faster and they're going to mount an attack faster. When they do this, usually they can wipe out the germ before a disease actually starts. Sometimes B cells can remember germs for a little while, sometimes they can remember them for your entire life. This is why some people, when they get infected with chickenpox, might never get it again for the rest of their lives. Their B cells remember the chickenpox virus, have antibodies ready to go, and if chickenpox ever shows up again, the immune system can wipe out the disease before it has time for people to get sick. This is called immunity. Immunity can show up a couple of ways. For example, if an infant were to breastfeed, they're taking up the T and B cells from the mother's milk. And during the time the infant's breastfeeding, it's actually going to be immune to a lot of the same diseases that the mother is immune to. The problem with that sort of immunity is that it's temporary. Now, the infant isn't making its own T or B cells in the bone marrow, so over time, once the infant stops breastfeeding, that immunity is going to go away. This is probably a good time to mention that when somebody has a severe allergic reaction, that's actually an immune response as well, but it doesn't usually involve the B or T cells. Basically, in an allergic reaction, what's happening is the body thinks that there's something there that doesn't belong there, some invader. So it responds dramatically to this, sometimes in a life-threatening way, because our bodies are screwy like that. So we've talked about a couple types of immunity. There's active immunity, when your B and T cells learn how to deal with a germ and you become immune moving forward. We've talked about passive immunity, when you acquire it some way, like infants through breast milk. And there's also a third type of immunity. It's called artificial immunity. But right before that, a quick bit about antibiotics. So in 1929, Alexander Fleming discovered pretty much by accident that penicillin prevented certain types of bacteria from growing. Seriously, it was a complete stroke of luck. He was investigating things that kill bacteria, left his lab a mess when he went on vacation, and when he returned, he found mold growing all over some of his equipment, and just by chance, he noticed that the bacteria wasn't growing in the areas that were moldy. He discovered it was a specific mold called penicillium, and voila, penicillin. This was a lucky accident that went on to save millions and millions of lives and continues to save lives even today. So cheers to you slobs out there. So a lot of antibiotics used today work the same way that penicillin does. So bacteria have this extra wall outside of their cell called a cell wall, and it makes them tough enough to survive inside the human body. So all penicillin does is it keeps the bacteria from building that cell wall as strong as usual. Today we use some other antibiotics. There's some varieties that can stop DNA replication in bacteria. If there's no DNA replication, there's no cell division, bacteria don't reproduce. We can safely take these antibiotics because we don't have cell walls and our cells don't reproduce the same way bacteria does, so it only affects the bacteria for the most part. It's important to notice that our immune system still has to kill and eliminate the bacteria for the most part, but the antibiotics give a huge helping hand. Okay, so here's the rub. Remember how viruses are just a little chunk of DNA or RNA inside an envelope or a membrane? Well, that means they don't have cell walls like bacteria do. They also don't reproduce on their own. They trick other cells into reproducing for them, so they don't do any DNA replication. So what effect do antibiotics have if you're sick with a virus? If you guessed nothing at all, you're absolutely right. If you're ever sick with the cold or a flu or any other disease that's caused by a virus and you're taking antibiotics, you're completely wasting your time, your money, and potentially life-saving antibiotics that someone else could have used. All right, it was a long and winding path, but we're finally ready to talk about vaccines. Okay, let's start with their gross history. So it looks like somewhere along the line in India or China in the 16th and 17th century, medical practitioners figured out that if they took the scabs off of people that survived a smallpox infection, they dried and crushed up those scabs into powder and then blew that powder into a healthy person's nose or rubbed it into cuts on their skin, that healthy person would then get a mild form of the infection most of the time, and that also meant that moving forward, they probably wouldn't catch smallpox or wouldn't die from it. Now, how the heck someone figured that out, I have no idea. Remember, this is long before the germ theory was common or accepted. All they knew is it worked, so they did it. Now, this was a big deal at the time because at that time, smallpox was common around the world and as many as a third of the people infected with it would die. We now call this practice inoculation, and it was far from perfect because as many as 2% of the people that were inoculated still developed a lethal form of smallpox and died. So most of the time these inoculations only occurred when there were outbreaks happening. So in 1774, an English farmer, Benjamin Jesty, caught cowpox, which is a less deadly but closely related disease to smallpox. He passed the cowpox to everyone in his family, everyone survived and recovered, and 15 years later they were all inoculated for smallpox. Now, the way people respond to an inoculation when it works is they get a mild form of the infection, so they get a little bit sick. But Jesty's entire family didn't get sick at all. They were already immune to smallpox. An English physician by the name of Edward Jenner made the connection. He saw the relationship between cowpox and smallpox, and he made a procedure for passing cowpox infections around healthy people, thus immunizing them from the smallpox infection. Jenner actually coined the term vaccine, and in his case, all the vaccine was a less deadly form of the infection that taught the immune system how to deal with the more deadly form before it showed up. Boom, vaccines are born, but vaccine can be a confusing term. Like how we're using the word germ to describe anything that's too small to see but can cause disease, and that might be fungus, bacteria, and virus. Vaccine is anything that can be given to someone to teach their immune system to be prepared for and immunize people for other diseases. So how does it do this? I'm glad you asked. So there's 4 main categories of vaccines that we use today. There's inactivated, attenuated, virus-like particles, and subunit vaccines. So an inactivated vaccine is basically just a virus or a bacteria that's grown in a lab, and then it's killed either through heat or through chemicals. Now what this does is it makes it inactive, but at the same time all the surface markers are still intact, so your immune system can still recognize it. Now remember how our immune system works. Our B cells are going to recognize that germ and keep antibodies around just in case it shows up in the future. But since the bacteria or the virus was already dead when it was introduced to the body, it doesn't cause the disease. Now an attenuated germ is basically one that reproduces slower or it's less deadly. It's basically a wimpy version of the germ that scientists have isolated. So the same thing happens. Our immune system comes in, it deals with the germ, and then it remembers what it looks like in case it ever shows up again. But there's 2 major drawbacks with this type of vaccine. The first is it could become a more dangerous version of that germ, and the second is if there's something wrong with your immune system already, even a wimpy germ can be deadly. Virus-like particles and subunit vaccines are basically just pieces of the germ. So it does the same thing, shows up, the immune system finds it, recognizes that it doesn't belong there, and then keeps some antibodies around in case those pieces show up again. The cool thing about those is because it's not a complete germ, there's no chance that it's going to make anybody sick. So in every one of these cases, an immunity is still the immune system doing all the work. It's just got advance notice, like it has the enemy's plans ahead of time. What's also important is we have to poke the immune system to make sure it actually responds to it so the B cell finds those antibodies for that disease. Sometimes the vaccines are not dangerous enough to get the immune system's attention, so we have to use something called adjuvants. Adjuvants are just chemicals that our immune system's highly responsive to. So when they're administered at the same time as the vaccine, it's more likely that the immune system's going to recognize the vaccine as a risk and then respond to it in a way that produces immunity. Also worth mentioning here is a lot of germs get completely destroyed by our digestive system. They just don't survive it. And in the same way, vaccines also get completely destroyed in our digestive system. So for the most part, they can't be ingested, they have to be injected into circulation. Now, special care has to be taken to make sure that when vaccines are being developed, that no germs or funguses grow in the vaccine. So every vaccine has multiple components. It has the wimpy germs or the germ components, it has the adjuvants, and it also has preservatives to make sure there's nothing in there that isn't supposed to be. So can vaccines be dangerous? Yes. Are the ones recommended by your doctor for your children dangerous? No, they're probably not. Let me explain. Now remember how I said some vaccines are just putting a wimpy version of a germ inside a person that teaches their immune system to become immune to a more dangerous version of that? There are definitely some people that should not receive that type of vaccine. If their immune system is compromised in some way, they could become very sick from it. Now if you have a normal immune system, that's not a risk. Now also remember how I said that allergic reaction is just an exaggerated immune response? Well, people can be allergic to all sorts of things. In fact, there are people on Earth right now that are allergic to water. That's right, they're allergic to water. It's also possible for people to be allergic to part of a vaccine. Remember, there's a couple of components. Now, if this were to happen, it's very rare and it's usually just redness or swelling at the site of the injection. In extremely rare cases, people can have a severe allergic reaction to vaccine. How often does this happen? Well, to give you an idea, in the 15 most commonly marketed vaccines in the US today, only about 1 in 450,000 doses results in an extreme allergic reaction, and those are hardly ever fatal. So it's extremely, extremely rare, and this is probably the worst thing that could happen when someone is vaccinated. So there are definitely some people who shouldn't receive some types of vaccines, and there are also side effects associated with every medication. But if your doctor is suggesting that you become vaccinated or that your children become vaccinated, it is safe for them to do so. Now, you may have heard that some vaccines can cause autism, and that's because there are very dangerous people in the world. They're called liars. So in 1998, British surgeon and medical researcher Andrew Wakefield had a study published in The Lancet, which is one of the oldest and most trusted medical journals in the world. The study seemed to indicate that there was a link between the MMR vaccine, which was for measles, mumps, and rubella, and autism. So what Wakefield claimed was a number of his patients started showing the signs of autism right after they received their MMR vaccine, which, if it was true, would be a really big deal. Now, it turns out it wasn't true. Now, the problem with publishing in a peer-reviewed journal is that your peers are going to review what you publish. Shortly after the study was published, a number of researchers from around the world tried to reproduce or confirm any of Wakefield's findings or conclusions, and none of them can find any correlation between the MMR vaccine and autism. A reporter for the Sunday Times did a little bit more digging, and he found a shady connection with Wakefield that indicated there might have been some financial gain for making some fraudulent claims about the MMR vaccine. So most of Wakefield's co-authors withdrew their support. So with typical blinding speed, justice was served. 12 years later, a medical tribunal found Wakefield guilty of 36 counts of violations. He was barred from practicing medicine in the UK, and The Lancet retracted the publication of his articles. Their editor-in-chief said that they had been duped. Now, since that time, even more evidence has turned up that connected Wakefield to a possible profitable venture if there was a connection between MMR and autism. And the raw data from his other studies seems to indicate that it's not the first time that he was dishonest about his research either. So Wakefield's kind of like a supervillain. And boy, did his research have an effect. So when his study was published in 1998, it was widely distributed, and parents, of course, were justifiably concerned. So vaccination rates in the UK and Ireland, and even here in the US, started to drop. So the CDC, the American Academy of Pediatrics, the Institute of Medicine in the US National Academy of Sciences, the UK National Health Service, and the Cochrane Library all went to scale with multiple large-scale inclusive studies to try and find a connection between the MMR vaccine and autism, and they found nothing. Meanwhile, decreased vaccination here in the US and in the UK have been linked to a number of epidemics and deaths, and Wakefield's report has been referred to as one of the most damaging medical hoaxes in the last 100 years. So how do we know vaccines even work? From the Journal of the American Medical Association and the CDC, here's a couple of charts that demonstrate the effectiveness of vaccines. This first table is comparing the annual number of deaths recorded in the US in the 20th century to the number of cases reported in the US in 2010. And we see in every situation where a vaccine is available, a drastic decrease in the number of reported cases. The next table is comparing pre-vaccine era estimated annual deaths compared to current estimates in 2008. Now, by the way, both 2008 and 2010 data doesn't necessarily reflect the effect of the anti-vaccination movement, but we see a tremendous decrease in the loss of life year to year from each of these preventable diseases for which vaccines exist. Now, for an even more dramatic example, let's take a look at this graph of smallpox deaths. This is a disease that was essentially eradicated from the planet as a result of an aggressive and collaborative worldwide vaccination program that was taken on in 1959 and accelerated in 1966. This last one was polio, pretty much eliminated from the US after an aggressive vaccination program was implemented. Vaccines work. They save millions of lives every year, and they eliminated a number of horrible diseases from the face of the planet. I've heard some people ask, well, couldn't it have been because of something else, like better hygiene and sanitation? Of course there are other factors that affect how rampant a disease is, and the most important of which are things like hygiene, access to potable water, indoor plumbing. All of those things, in addition to a healthy lifestyle and exercise, keep most people out of illness and in health. But none of those things, individually or combined, explain our improved control and management of these diseases once their vaccines became available. Now, it's worth pointing out that even today there are still parts of the US that don't have access to indoor plumbing, that still lead unhealthy lifestyles and are unhygienic, but that didn't stop vaccines from eradicating smallpox and polio from the face of the earth. Now, on the flip side of that coin, we're seeing well-educated and affluent communities of people who chose not to vaccinate their children get affected by epidemics of preventable diseases that were almost unheard of in the US as little as a decade ago. Well, don't big pharmaceutical companies just want to sell a lot of vaccines so that they make more money? Well, let's only look at the flu vaccine. The flu vaccine for all of the big pharmaceuticals accounted for about $3.1 billion of revenue last year, which sounds like a really big number. But when you take into account all the revenues of big pharma last year, which was about $1 trillion, that means vaccines generate about 0.3% of all revenues for big pharma. There are plenty of medications that drive more revenues for big pharmaceutical companies. There are lots of other factors that need to be taken into account there. For example, vaccines tend to be the lowest profit margin of all drugs produced by pharmaceutical companies. There's shipping and spoilage losses, and in the case of the flu vaccine, at the end of every season, whatever's not sold has to be thrown out, so there are huge losses to the pharmaceutical companies. If big pharma was only profit driven, they would actually make more profit by not producing vaccines. And finally, it's not big pharma that's promoting that we get children vaccinated. It's public health organizations like the CDC and academic organizations all around the world that don't stand to profit at all. So now the sad part. There are life-threatening and potentially crippling diseases that are also preventable, that are a threat to communities here in the United States again. Vaccines work for people, especially people with normal immune systems. There are some people that might be at risk, but your doctor can identify this and inform you accordingly. Also, there are situations where people can respond very negatively if they have an allergic reaction to a component of a vaccine, but that's extremely, extremely rare and can also be anticipated by your physician. An important point to understand is vaccines are not 100% effective for the life of the patient. What that means is that sometimes someone can develop an immunity and lose that immunity over time, or in some cases, the vaccine might not take at all. For example, people that receive the MMR vaccine become immunized to rubella at about 85%. That means 15% of all people that receive the MMR vaccine can still become infected by rubella if they're exposed to someone that's infectious with the disease. So what we can do is break up every population into three groups. There's an immune group that was either exposed to the germ naturally or received an immunization through a vaccination. The second group of people have never been vaccinated and never been exposed to the germ, which means they could be infected. And the third group are people who are infected and infectious, which means they could pass along the germ. So during vaccination campaigns, the goal isn't necessarily to vaccinate and immunize everyone. The goal is to vaccinate enough people that group 1 is big enough that when infectious people are around from group 3, the likelihood that they're going to run into someone who's not immune but not yet infected from group 2 drops to almost zero. So this is what happened with smallpox. We didn't vaccinate everyone on the planet, but we vaccinated enough people that there were enough immune individuals in group 1 that the infectious people couldn't infect anyone from group 2, the people who weren't immune. The smallpox virus had nowhere to go, and so smallpox died off. This whole concept is called herd immunity. So the danger we face today is in the fad coming from the anti-vaccination movement. Parents are making decisions based on very poor information. Thinking that they're protecting their children, parents are opting out from receiving vaccinations for their children for highly preventable diseases that are also highly infectious, debilitating, and potentially lethal. By doing this, parents are essentially taking a gamble. The hope is their children won't run across anybody who is infectious and be surrounded by people who are immunized, but at the same time not risk the negative effects of having that vaccine. The problem with that decision is it's extremely selfish and it puts everyone at risk. As the number of people in group 2, people that could become infected, grows, the likelihood that infectious people are going to pass on the infection and start new epidemics grows higher and higher, and even vaccinated people could potentially become infected. Parents, if your doctor tells you your children should be vaccinated, listen.